Now, once again, I invite all of you to understand the concept of differentiation of implicit functions, which is related to exercise 5.8 of our textbook. So first, to understand what is the differentiation of implicit functions. Till the exercise 5.7, it was clearly distinguishable that y was a function of x. For example, y was sine x, y was sine x plus x square. So it was clearly distinguishable that y is the function of dependent variable x. In that case now, so sometime what happens that it is not clearly distinguishable whether y is the function of x or x is the function of y. For example, we have y, we have sine x plus y with tan xy equals to x upon y squared. Now it is not clearly here distinguishable that whether y is the function of x or x is the function of y. But our need is to find in most of the cases y as a differential of y with respect to x. Then what to do, how to deal this. So if you remember my earlier concept of differentiation of implicit functions, let us take example of, suppose we have sine x square and we differentiate with respect to x. So according to chain rule of differentiation, first you reach here, assuming this as an x, but there is no x, then you reach here and x square is differentiated as 2x. But if suppose it is d dx of sine y square, and for ultimately all our phenomena in differentiation, we assume that y must be the function of x. Then when you come here to differentiate, then since differentiation is taking place with respect to x, so this is taken as an x, because differential of this function with respect to x, so this differential operator recognize this function as a function of x. So it will assume here, suppose there is x, so it will differentiate into cos, assuming here we have x but we don't have x, we have y square. So now your differential operator will reach here d dx of y square. Now it will be seen as cos y square d dx of y square. So it is nothing but cos y square. Now it is treated this as x. So 2, but there is no x, there is y. Then your differential operator will reach to this y and that is dy dx. To distinguish, now like for example, if we continue this question like this, so d dx later reaches here as we are reaching here, but here differentiation of x is taking place with respect to x, but here differentiation of y is taking with respect to x. So here what happens, it is nothing but cos x square with 2x and d dx of x. To see the difference between these two things, since differential of x with respect to x is 1, so that's why you see this in a end cos x square into 2x, but here you get this as an end element of this step. So what we understand, if differentiation of some function is taking place with respect to a variable which is also found inside the function, then in end the step goes like this. But if differentiation of this function is taking place with respect to x, but in the function some other element is there, then in the end what we write, dy dx. Same way, if I write d dy of sine x square, so this is nothing but when you start differentiation by the chain rule, so it is cos x square, then you reach here d dy of x square, and it is cos x square. Since the function and the variable about which you are differentiating are not same, so it is nothing but 2x and dx dy. So remember one thing, that whenever a differentiation of function is taking place with respect to another variable, the function is not made from that. So in end always this kind of element is found. So that was the introduction of implicit functions. See few more examples. One more thing you should remember, that if one has to find dy dx, that is found for the y as a function of x, and if one has to find differential of x with respect to y, it is found from the function of x with respect to y. Another example to understand this, suppose we have to find differential with respect to x of the function sine xy, and here it is not distinguishable that y is a function of x, x is a function of y, but by default since we are making differential with respect to x, so you can say that from this idea, if differential of this function is made with respect to x, so actually y must be the function of x. See what happens. When you start making differentiation by the chain rule, you strike here, that is taken as an x, because always your differential operator recognize this place as this variable. So this xy is taken as x. So cos x, but there is no x. Instead of x, there is xy. That's why it is reaching at this place. Which is reaching? The differential operator ddx over xy. Remember, since you are making differential with respect to x, so actually you have to assume that y is a function of x. So now here x is a variable and y is a function of x. Here product rule will help us. How? X differential of y with respect to x and y differential of x with respect to x. So it is cos xy with x dy dx plus y into 1. So that is a differential of this function which already has a term of dy dx. If suppose we are given with the question sine xy equals to x square, this question, so you apply the differential operator over this entire question, sine xy equals to x square. So on this side it will remain, on the left hand side, that means differential of this function, you may take the help of this step, that means it is cos xy x dy dx plus y, and on this side since differential of x is taking place with respect to x, it is 2x. So from here you can evaluate dy dx is leaving on this side, and it is nothing but (2x sec xy minus y upon x after simplification). So that is the if question. This is known as, these kind of functions are known as implicit functions, where it is not possible to distinguish whether x is a function of y or y is a function of x. Precisely, you can say. So since in a crude language you can say that x and y are in a mixed form, so answer will also be coming in the same mixed form. So that is an answer of such question. One more thing I have to explain, that from the first principle method, that dy, just this thing already I have told you in my previous lecture. From the first principle method, it is delta y upon delta x. So as I have told you, here y is a change due to change in x. If you bring it down, delta x upon delta y, since both delta x and delta y are tending to 0, here being in denominator, you can write delta y is not 0 but very small. So this kind of expression, you can say that a first principle method of, this is the first principle method of y with respect to x, and this can be the first principle method of x with respect to y, dx dy. So you can say that differential of any function of y with respect to x is reciprocal to the variable x with respect to y. Or you can say that differential of y with respect to x into differential of x y is always 1. Remember that we are not cancelling, actually it is due to this particular result. Now to start with the exercise 5.8, I would like to take a question number 4, second part, which is this one. Now we have to find dy dx, that means differential of y with respect to x. That means we have to assume here y is becoming the function of x, because rate of change of y with respect to change in x, or the change in y with respect to change in x, is always due to this kind of function where y is dependent over x. Because when y is dependent over x, then change in x will result in change in y. So in this question we apply differential operator 2x 3y equals to sin y. See the process carefully. D dx operator will go to all these functions, d dx of 2x, d dx of 3y, d dx of sin y. Now here you will see that differential of all these parts are taking place with respect to x. So it is 2 dx upon dx, it is 3 dy dx, and here d dx will strike to sine, assuming this as nx. So it is cos x, but there is no x, there is y. Then your d dx operator is reaching over y, that is d dx over y. So now it is dx upon dx will be 1, and this element will go on that side. So cos y minus 3 dy dx. So you can say that differential of y dy dx is 2 upon cos y minus 3. Like this we deal such question. Now I would like to take question number 8, third part. This one, as you are seeing, you can also consult from your book. So to find dy dx, we apply the differential operator over this question, x upon y, x square minus y. Remember, on this side both x and y are coming, and since we have to find dy dx, so we have to assume that y as a function of x. So here d dx will go to all the components of this question separately, like d dx is going over x upon y, d dx is going over x square, d dx is coming over y. So we have to find out what dy dx. So now we have to differentiate. We have actually it is made from 4 components, 1 2 3 4. So I am starting here. Now d dx is striking over sine, so assuming this is an x, so cos xy. You can take the help of the part which already I have taken here in this video. So d dx will reach here to xy, then it is x dy dx, and y differential of x with respect to x is 1. And here, since x is the variable, y is the function of x, that means both are variable. So here the quotient rule will be applicable. That means y square y differential of x is 1, and x differential of y with respect to x is dy dx. On this side it is 2x minus dy dx. Now there is we need the instead of calculus we need the algebra here to collect the dy dx term on same side and non dy dx term on the right hand side. See how it happens. Y x cos xy dy dx y cos xy plus 1 upon y x upon y square dy dx 2x minus dy dx. Now bring all the dy dx term on this side. So x cos xy plus x upon y square dy dx plus 1 dy dx. What I have done? I have taken this term, and this term on same side. I am sorry, it will remain minus because it is on the same side. And rest of the terms are sent on that side, that is 2x minus this goes on that side, it is without x dy dx, and this goes on that side minus 1 upon y. So finally our answer will be dy dx is this whole, that means 2x y cos xy 1 upon y whole divided by x cos xy x upon y square plus 1. That is the answer of this question. You can see this entire solution once again. I think some part was because of reflection was missing. One more very important question I want to bring, that is question number 7, first part, where this is the question where you have to prove differential of y with respect to x into differential of x with respect to y. This product is always 1. So we need to find first to find dy dx. So what to do now? Or entire this question x cube y cube 3axy, we apply differential operator ddx, because to find dy dx we need to apply the operator ddx. Understanding or not? So what happens? It is 3x square because here is x and there is x. But when we reach here is y, but differential is taking with respect to differentiation is taking place with respect to x. So first it will treat normal, but then ddx will reach to, for example, it is y whole cube ddx. So first ddx will strike here, assuming this as an x. So it is 3, but it is not x, it is y, it goes inside. Which goes inside? ddx over y. So it becomes, so it is 3y square and dy dx. Now this can be removed. Then on this side, 3a being constant, but we have two things, x into y. So x is fixed, differential of y with respect to x is dy dx. Now y is fixed, differential of x with respect to it is 1. So now 3 can be common and cancelled, and then dy dx will be nothing but y square minus ax equals to y minus x square ay minus x square. So it becomes dy dx equals to ay minus x square whole upon y square. This is suppose 1. Now we have found dy dx. Well, we need to find dx dy. To find this, we need to apply differential operator dy. We need to apply differential operator dy over x cube y cube is 3axy. So now it is 3x square with dx dy. Reason is here x and with respect to y is taking place, but it will remain only 3y square because y is with respect to y. On this side being 3a constant, we differentiate x into y as a product rule. So x is fixed, differential of y with respect to y is 1, y is fixed, differential of x with respect to y is dx dy. 3 being common and cancelled. So finally dx dy is x square minus ay equals to ax minus y square. So dx dy is nothing but ax minus y square whole upon x square minus ay. So we have, this is the value of dy dx and it is a value of dx dy. Putting them here, dy dx into dx dy equals to dy dx is ay minus x square y square minus ax. Now putting the value of dx dy, I am taking minus sign common from numerator and denominator. So it is y square minus ax and ay minus x square. You will see them, they are cancelled completely and this one. Hence, this is proved that, as earlier I have proved also this result in my previous session. So this part is also proved.